I mean, just look at this thing. It's an absolutely incredible piece of engineering that keeps our lives running, usually completely out of sight. But how does it do it? How does it take simple steam and convert it into the electricity that lights up our homes? Well, today we're going to go inside and find out.
All right, so before we start taking this thing apart piece by piece, we really need to wrap our heads around the core principle. At its heart, a steam turbine is just a masterful energy conversion device. It all starts with the simple, elegant process of turning heat into motion. This diagram gives us the 10,000-foot view. You've got a heat source, like a massive boiler, creating a huge amount of high-pressure, super hot steam. That steam is basically the fuel. It gets piped directly into the turbine, which you can see right there, that green component in the middle of it all. And this conversion is the entire point. You know, think about a little pinwheel. The energy from your breath makes it spin, right? Well, a steam turbine does the exact same thing, just on an unimaginable scale. Instead of your breath, it uses incredibly hot, high-pressure steam to spin a multi-ton rotor made of solid steel.
And here's that pinwheel idea, just on an industrial level. See the red arrows? That's the steam. It first blasts into what's called the high pressure, or HP section. As it expands, it pushes its way through row after row of these perfectly shaped blades, forcing the whole thing to spin at thousands of revolutions per minute before it moves on to the next section. Okay, so now that we get the basic idea, let's dive in and really see the components that make this amazing energy conversion happen. We're going to take a look at the anatomy of this metal giant. Think of this cross-section as our roadmap. Steam comes in through the inlet and starts this long journey through a complex series of stages where each one is designed to squeeze out just a little bit more energy. So let's break down the most important parts. So all the real work gets done by this perfectly choreographed dance between two main parts. First, you have the nozzles, which are stationary. They take that high-pressure steam and squeeze it, converting all that pressure into pure speed. Then, that high-speed jet of steam smashes into the buckets, sometimes called blades, which are rotating. That impact is the force that spins the whole rotor.
So, where are these stationary nozzles held? Well, they're mounted inside a part called a diaphragm. You can think of the diaphragm as a big, solid partition that separates each set of rotating buckets. Its whole job is to hold the nozzles and aim the steam perfectly onto the next row of buckets. And here you can see exactly how this all fits together. On the right, that's a close-up of one of those diaphragm assemblies. You can see it's built in two halves. And then on the left, you can see where those diaphragms slot right into the main turbine casing, sandwiched right between the rotating stages.
And all of this brings us to the rotor itself. It's truly the backbone of the entire machine. It's this massive central shaft that holds all the rows of moving buckets. Every single push from that steam gets collected by this rotor, and it all combines into one incredibly powerful spinning motion that's going to turn the generator.
Now you might be thinking, okay, you've got this huge rotor spinning at thousands of RPM inside a stationary casing, so what keeps all that high-pressure steam from just leaking out through all the gaps? The answer is a really clever piece of engineering called a labyrinth seal. If you look closely at the inner ring of that diaphragm, you'll see those tiny little teeth. Those are the seals. Now, they don't actually touch the rotor. Instead, they create this really complex, winding path, like a maze. As the steam tries to get through, its pressure drops at every single ridge, which drastically cuts down on leaks, all without any physical contact or friction. It's brilliant. So we know how it works when it's running. But a machine this enormous and precise can't just be flipped on like a light switch. It has to be brought to life carefully, methodically. This is the startup sequence.
The very first steps are arguably the most critical ones, and they happen long before any steam is even let into the turbine. First, the turning gear gets engaged to start slowly rotating the shaft, and then the lubrication system kicks on to protect the bearings.
Take a look at that turning gear up in the top right. It's a pretty small electric motor, and its only job is to slowly rotate that massive rotor. Why? Because if a rotor this heavy just sits still, its own weight will cause it to sag or bow just a fraction of a millimeter. And believe me, that tiny bend would be absolutely catastrophic at high speeds. The turning gear makes sure it stays perfectly straight while it warms up.
At the same time, the lube oil unit roars to life, pumping tons of oil to all the bearings. This creates this high-pressure film that actually lifts the entire multi-ton rotor, so it's basically floating on a layer of oil. This allows it to spin with almost zero friction. Simultaneously, the massive outer casing has to be heated up uniformly. If one part gets hot too quickly, the whole machine could warp. So steam is introduced very slowly to heat the metal evenly, while special sprays in the exhaust hood keep the cooler, low-pressure end from getting too hot. It's an incredibly delicate balancing act.
From that slow, careful start to a powerful, roaring spin, this intricate dance of steel and steam has been the backbone of our electrical world for over 100 years. It's a true testament to incredible engineering. And it leaves us with a pretty big question. What engine will power our next 100 years?